Okay, I'd like to start today, or we like to start today with Rudolf Triebel from DLR at close to Munich, right?
Yeah.
Okay, but yeah, and also as I started on Monday, Rudolf and his group is going where no robots has gone before. And his last article in his publication list is, or the last ones are about bringing autonomous robots to Phobos, and I'm really excited about it. And yeah, thank you for being here. And now you can take over.
Thank you very much. Does the microphone work? Very good. Yeah, thanks for the introduction. Unfortunately, I'm not showing too much on Phobos today. I'm sorry. We can later in the discussion, I can tell you everything about the Mars moon, right? It's not a moon, it's not a Mars, it's the Mars moon. Again, I'm not showing anything today. Well, one slide video, but not on Phobos. Okay, yeah, the presentation today, as you can tell, is already about perception, right? We're talking about perception, and mainly there's one important part in perception, which is the treatment of uncertainty, which is one of our main research topics that we work on in my group. And I'd like to start with this kind of motivation. Imagine you have a fancy, shiny robot in your home environment, right? And now you want to use it, right? It should be useful. You should be doing things with it, like cleaning up or, I don't know, setting table or whatever. And now, of course, what this robot has to do is interact with the environment, right? Manipulate, like pick up things and put it from one place to another place, right? And to do that, of course, it needs to solve many problems, and especially problems in perception. This is the topic I'm going to talk about today. So the first thing is it has to see what it sees around, right? And it has then to answer certain questions. And these questions I'd like to show you in this example here, right? The first question might be, what is that, right? And that question is already not so easy, right? We as humans, we would say, well, I mean, a banana, right? But that's also not the only right answer, right? It could also be a table, right? It could also be a correct answer to that question, right? Another correct answer would be a banana on a table, right? So this already gives us the hint that it's not so easy to actually define what that actually means, right? What we mean by that, right? That means we have to segment the object around and first of all, know what an object is and where object boundaries are before we can actually classify this object, right? This is the first question. The second question is, if you want to grasp it and if you want to do things with it, you should know where exactly that position is of that thing, right? So you have to have an orientation and a translation of that object, right, in 6D. Otherwise, you cannot place your gripper or your hand exactly on the object, right? You cannot do this because you have to exactly know where this is. For us humans, this is easy, but for robots, it's difficult because you have a projection, right? You have a 2D image from a 3D scene, and it's not so easy to find the distance of the object and to actually know where you place your fingers. And the last question that I'd like to ask is, how can I grasp it, right? So where do I actually put my fingers to have a stable grasp, right? For us, again, seems easy, but there's so many possible positions. Maybe in this example it's easy, but there's many other objects where it's hard, right? So where do I actually put my fingers such that if I lift this object, it doesn't fall down, right? So how much pressure do I have to put on, and where exactly do I put the fingers? So these three questions I'd like to summarize in these kind of three topics or tasks that we have in perception. The first task is object detection. Object detection means that I have an image and I want to have either a bounding box or a segmentation or whatever that tells me where this object is, right? And this often means that I have to segment, first of all, the scene, right? I have to tell foreground from background, right? Which pixels correspond to the object and which don't. And then I have other things like feature extraction and so on. And in the end, I need to do some classification, right? This is a classification problem. I need to assign so-called semantic information, right? I give the scene a name. I give or this object a name. I say, this is cup or this is whatever, right? And it's done usually by assigning class labels. You have natural numbers to do that. And to do that, of course, you require color, texture, any kind of like these visual features that you can do to actually do classification. The second task is object pose estimation, right? Here we have actually a regression problem, not a classification. Here we want to find an orientation and a translation of the object, right? And what this does is it retrieves the exact position of this object in the camera or in the robot frame, right? From the robot on, I want to know where exactly this object is. And it can be done by at least two kinds of approaches. One is the so-called frame-by-frame approach, where in every single frame you find the orientation and position and translation of this object, right? You do this over and over again. Here in this paper we show a recent work how this can be done. This is a benchmark data set where this works quite well. And the other approach that you can do is tracking, right? You just have one image, and at this very first image you kind of guess where the object is, and then you kind of follow the object from one frame to the other, right? You have one frames that follow each other, and then you say, well, in the next frame the object is not very far from the first frame, and that means I just have a local search around the current position, the current estimate of the position of the object, and I just guess and then compare my predicted position of the object with the true color histogram, whatever I have of the scene, right? And this works also quite well. We have also a paper on that one. So these two methods actually show that you can do pose estimation quite efficiently. And of course, you can combine the two, right? You can use this one first to estimate the initial position, and then from then on to tracking. And of course, then you have to make sure that you don't lose the object, right? So when there's occlusions, or when the camera goes out of the scene and everything, then you have to, of course, have something that tells you that you don't see the object anymore, and then you trigger again the frame-by-frame thing. However, to do that, of course, you need the exact geometry of the object, right? Otherwise, you cannot tell exactly where this object is, because if I don't know what the object looks like, how can I then tell what's its position, right? And the last thing that we need to do manipulation is, of course, the most important thing is grasp detection, right? Where do I put actually my fingers to do this grasping task? And this again is a regression problem, right? I need, again, a position and an orientation of my gripper. And it also requires the exact geometry and kinematics now of the gripper or the hand or whatever I have, right? So of course it requires more information. Now, if you look at these kind of three tasks and we look closer to them and really ask ourselves what is really required to do manipulation, right? If we want to pick something and place it somewhere else, is it really that we need all that? And if we look closer, then we find out that the first two are actually not that much required. I mean, they're nice to have, it's cool to have these kind of methods, but in general, you might not actually need that. And I'll show you in a second why this is the case. So object detection, we don't need to know what the object is if we just want to place it from one position to another one, right? I mean, if the robot just cleans everything up that is in front of it, right, it doesn't need to know what these things are, right? It doesn't have to have a notion of banana or object, whatever. It just like picks things and places it somewhere else. However, of course, if you want to tell the robot that it should do that, right? If you do HRI and say, robot, please pick me the banana and put it somewhere else, then of course I need the classification, right? I need the semantics to tell the robot what the banana is, and the robot needs to know what this is, right? This is of course true. The second thing here, also the pose estimation, is not really necessary as long as I really put my gripper at the correct position, right? If I don't know where the object is, but I see that there's something lying in front of me, I can just put my gripper where that thing is, right? And then grasp it without actually having a pose of this object, right? So this is also not really required. However, if I want to do functional grasping, right? If I want to use the tool that I have there and put it and grasp it with a certain grasp, like for example a spray bottle, right? Where I want to use the spray bottle and use it in a certain way, then of course I need the pose, of course, of that object because I need to exactly know where to put my fingers on that spray bottle. And the last thing is, of course, required. This is the key thing, right? Grasp detection is important. Otherwise, I can't do any manipulation. Now, the common pipeline to do this is this one here, right? So you have an image, and you do some detection here. Then you get your bounding box, right, that I just showed you. And then you do pose estimation, right? You have the 60 orientation of this thing. And then, yeah, maybe you do some grasp detection, and at the end, you execute the grasp. In the case that this object is known, that we have semantics, we have geometry, and we know everything about the object, if you really think about it, you don't actually need the grasp detection, right? This is actually the opposite case, right? If everything is known, then you just know where the object is, and you already know a good grasp because you know the object, right? And that means you can then project this good grasp to the object and say, well, I mean, if the object lies there, and if I know the position of that object, then I just like project my grasp there, and I don't have to detect a good grasp, right? Now, before I go to the unknown case, I tell you what are the main problems in all these kind of 3 tasks, right? And I think there's at least 3 major problems that we have with these tasks. The first one is that, like most of these tasks, they are so-called inverse problems, right? Inverse problems means, and this is a very nice illustration here from John O'Brien, which appeared in the New Yorker in 1991. This is just an image that shows the projection, right? So it shows you that you have a projected image here, and if you look at that image, you might say, well, this is a hand, right? Of course, it's a hand. But if you look at the scene, it seems not to be caused by this hand. And this is the problem, right? So we have a cause and an effect. And very often in computer vision, we have the effect, but we have to go back to the cause, right? We have to say, what's the cause for this given effect? And because this is a projection, we cannot invert that easily, right? It's an ill-posed problem. We cannot just say, well, this must be a dancing bunny, because it's very unlikely that this is a dancing bunny, right? So this is one important problem in computer vision. And object detection and grasp detection are also inverse problems, right? We have the same issues there. And the second important question that we have is, how do we solve the so-called open world assumption? And the open world assumption, I think, is key in robotics, right? You have to assume that whatever you've observed so far is not everything that is around there. There's always something that you might not have seen and that you have to take into account in a certain way, right? There's always objects that you don't know, and you have to deal with them. You have to be able to deal with unknown things. That's one thing. And the other thing is you have to tell apart the unknown from the known, right? You have to know that something is unknown, and you have to say, well, this is something unknown I haven't seen. I have to deal with this differently from all the other things that I know, right? This is not so easy, right? This is the key question. How do we distinguish the things that we know already from those which we don't know, right? And the last thing is, of course, real-time constraints. This is the video that I promised you. This is our rover that's not going to Phobos, but it's similar. It's a planetary exploration rover. So this is actually Mount Etna. It looks pretty much like the moon. That's on purpose, of course. We wanted to have a system that works in these kind of environments. And it can grasp these objects here, basically with the same idea that I showed before. So it can grasp unknown objects, right? And put this into this basket here, and then bring this away. What you see here is, of course, that it's not the fastest thing. It's a very fast robot, right? Compared to other planetary robots, it's very fast. Still, of course, you can imagine that whatever we want to do in perception, we have to be as fast as possible, right? This is just the message behind this here. It's also interesting to know that the bottleneck nowadays is not the perception anymore, right? Perception parts are quite fast already, so any other things are slower. But still, of course, as perception people, we have to be as fast as possible. We cannot just take. And of course, memory requirements and all the kind of things. We have to be careful here that we don't block the whole system. Okay, I'm going to talk about the first 2 things, right? Inverse problems and open world assumption. How do we address these now? So the inverse problem, the idea to address that is to so-called fill this gap, this information gap, with data, right? So what we do is we observe very often certain pairs between causes and effects, right? For example, object appearance and object labels. And if we have enough of them, then we can relate them statistically. We can say, whenever I saw the dancing bunny, then I saw this shadow. And that means if I have seen enough dancing bunnies, then I can reason that this might be not a hand, but a dancing bunny. And if I haven't seen any dancing bunny, of course, then it's more likely to be a hand or something else. Right? This is the whole point of machine learning, and this is the reason why we do machine learning, because this kind of helps us to address these kind of inverse problems. Okay, so that means we can train a model, right, that can predict causes from given effects. And we do this, of course, with our fancy architecture. This is just one abstract illustration of a deep network. It can be any fancy network that you want to do, right? You have your feature extraction. In the end, you have some classification here, standard things that you have to do. And what you have to do this, you train this with images, right? You have an image of a tennis ball, and you have a label, tennis ball, and then of course you compare the prediction with the ground truth, and then do gradient descent and everything, and so you optimize your loss function in the way that this matches, right? So this is the classical thing of doing learning, right? The thing is that you need enough data to do that, right? Enough means like millions or whatever. It's really lots of examples to actually be able to do that, right? So this learning-based approach has this kind of counter side that you have to have the training data. And to get good training data in robotics, it's not so easy. And therefore, what we do is very often we generate our training data ourselves, right? We generate synthetic training data. And I'd like to give you an example how this looks like. Now, for the case of the of the grasp detection, not for the object detection. So this is a recent example of a work where we trained to grasp unknown objects, right? So this is the way we do this. So here first we start with a physics simulator. It's called Acronym. It's a nice name for a data set. And in this data set we have 17.7 million grasps that we've tried, right, in simulation, right? We have a cup, and then we grasp the cup in simulation, and then try and you see sometimes the grasp falls, and the cup falls, and sometimes it doesn't, right? And by that we can then tell the good grasps apart from the bad ones. You can simply say trial and error, which is a good grasp and which is a bad grasp. Then from that, what we can do is we project these grasps onto a virtual scene, right? We generate scenes in 3D, right, with objects and so on. And these green lines are now potential grasps of our two-finger gripper, right? So where can we put the finger gripper on the object? And then, what kind of grasp would that be? Is it a good grasp or not? We know this now from this training data. And now we have enough to do training, right? We can now relate one to the other and can say, well, if I now render this scene in a depth renderer, so I have the scene as it was in the real sensor, then I can train this, right? This is the input to my neural network, and the output simply compares the predicted grasps from the ground truth grasps on these objects, right? I have to, of course, make this efficient. The trick here is how these grasps in 6 degrees of freedom can be efficiently represented. In this work that we did here, we actually project it onto 4D, right? We have a way to reason in terms of contact points, right? So we have a point cloud of the object, and the point cloud can be separated between good contact points and bad contact points. I'm not going too much into more detail, but the trick is here we can do that, right? We can do this efficiently so that we can then learn grasps for completely unknown objects, right? There's no semantics whatsoever in here. We don't know what these objects are. It's just geometric. That's just physical scenes, right? Just objects lying around without any name, without any semantics, right? That means from the standard pipeline that I just showed you before, right? This is this standard pipeline of known objects where everything is given, right? We know the geometry and everything. We are now canceling these first two things because we don't know this, right? We don't know the geometry. And we get away with this problem of object blindness. Object blindness means that some objects might be detected because those are the ones that we have learned. Others we don't know, and that means we don't detect them, right? So if we run the camera over the scene and then certain objects, also in the videos that I just showed you before, you might have seen the cup is detected, but everything else is not detected. Of course, because we haven't trained on that, right? And this will always be the case. There will always be an object that we haven't trained on and will not detect that. With this, we don't need that, right? Because we don't actually care about what these objects are. We just say, just give me everything that's lying around, right? So this kind of addresses that object blindness problem. So the new pipeline is now the following. We have an image, and all we do is we segment that image, right? And at the same time, we do grasp detection, right? We find good grasps on the scene, not on object, but on the scene, right? And we can then segment objects or things from other things, right? And then execute the grasp for a certain segmented thing, right? Which is then in this case the banana. And the way this looks like is here. So this is the video that I show you for that. Here on the left side you see segmentation, right? This is a recent approach that we developed in my lab. Actually, Max Dorner did that. He's sitting around here. So here, this is just segmentation of unknown things, right? You just segment everything that you see in front of you. And here you project the estimated grasps, right? These are in the image here now. And now you can say, well, if this is one segment, and if there's a good grasp on that segment, then just execute that grasp for that segment, and then you pick that object, right? And this is what's shown here. So this is our experiment with this LBR arm that is on this linear axis. It just picks everything away, right? Sometimes it doesn't work, as here, but then it just tries again, right? Because it still sees things in front of it. It says, well, there's stuff. Get me away with the stuff, right? So this is a cool cleaning up robot. And it also works here with piles, right? If you pile up things and you have occlusions, then you don't care because you just take the next best grasp, right? And it could be something that is below. Then things fall over, of course, but why not? Okay, this is the first part, right? This is the inverse problems and how we solve that with learning. The second most important question is, how do we know that an object is unknown, right? So far, in this scene that I just showed you, everything is unknown, and that's easy, right? I just assume that everything is unknown, and then I don't have to distinguish it from the known thing. I don't have to react differently between the known and the unknown things. But actually what I want to do is have a clever algorithm that tells me, well, this is something I know, I do this completely different, I have a different grasping task for that known thing than from the unknown one, right? But before that, I have to tell apart the known from the unknown. I call this the known, the unknown, and the known unknown. The first idea to do that is very simple. I just have a distance measure, d, right, that measures how far am I away from a class, right? So I have a new sample x star, right? This is a new object that I observe, and I have a given number of classes, c1 to ck, and I just have some kind of distance that tells me this is that far away from that class. And the intuition behind that is if this distance is small, then the object x star is of the known class I, and otherwise it's unknown, right? That's a very simple approach, if then else. The problem here is finding a good threshold is very difficult, right? So the one threshold that you will never find that works for everything, this is not possible. It depends on the number of classes, right? The more classes you have, the smaller must be your distance or whatever that you might have to adapt your threshold and all these kind of things. And it also doesn't consider, for example, the underrepresentation, that some classes are appear less often than others and so on. And this is probably not so easy. The second approach is already a bit better. There, what we do is we actually use probabilistic reasoning, right? So we have a distribution. We call this distribution the predictive distribution, right? We have a distribution of y star given x, y, and x star, where x and y are training data. These are the known things, right? This is what I'm doing in the training data, right? That's just basically a bunch of features and corresponding class labels. And then I show the system the new object x star, and I want to have a distribution that tells us how likely is it that this corresponding x star is of class Ci, right? So the predicted label of that object that I have is of class Ci, right? And this probability I want to compute. And the intuition behind that is if this probability is high for a certain class I, then the object is known, right? Then we can say x star is of known class I, otherwise it's unknown, right? Now, the advantage of this over the other one is now finding a threshold is easier because now it's a probability, right? Now I can tell you what's the probability of, let's say, 80%, 90% that this is a known class and everything else is unknown class, right? This is easier to do. However, it leaves us with the question of how we can compute this predictive distribution. And in the literature, there's many, many ways of doing that, and I'm showing you 3 of them, right? The first simple one is you just use the so-called predictive entropy, right? The idea behind that is you do already have some kind of probability in the end, right? It's at least a value between 0 and 1, right? This is the softmax layer, right? Which comes from this logistic sigmoid. It's basically nothing else than logistic regression, right? You have this vector at the end that is as wide as you have number of classes, and for every class you have just a value between 0 and 1. And that means you can kind of say, well, it's something like a probability, right? Of course, it's not a probability, but it's a value between 0 and 1. And that means you can use those values, those pk values, which come out of this prediction, and compute something called the entropy, right? And the entropy, as we know, is something that we can interpret as uncertainty, right? The higher the entropy, the more uncertain is the prediction, right? This is basically this intuition behind that. You can think of this as the coin flip example. If you have a coin with two sides, and if the coin is fair, then the probability that the next thing is that next thing happens is 50%, and this is the highest uncertainty, right? This is the uncertainty 50%. However, if the coin is not fair, right? If one side is just happens more often than the other one, then you have a lower uncertainty, right? You have more knowledge about what comes next, and that means the entropy is lower and the uncertainty is also lower. Okay, the next idea is to use so-called Monte Carlo dropout. Monte Carlo dropout is a regularization technique used in training, right? People did that in training, but now then people started doing that also in inference, right? So this is very clever, right? A very nice idea. The interesting thing here is that people started doing that before they actually knew what this actually means, right? Then there came Yarin Gal with his thesis and proved that this is actually a good approximation for a Bayesian neural network. So doing that is actually quite clever, right? And you can actually mathematically prove that, but people did that before they could prove it, right? This is interesting. So how does it work? So you have your network again, right? And then in the inference step, right, you run several forward passes through the network, right? And for every forward pass, you cut out certain weights, right? So for example, you have a 50% dropout rate, right? And that means every second weight is just cut down. That means you set it to 0 and then run the forward pass and do this for a number of these, right? So every time you cut other weights, right? And then you run again the forward pass, and that's every run through the network is a sample. And in the end, you have a number of samples, maybe 10, 20 or something like that, not many you need. And then you can do some statistics, right? Mean and variance over the samples, and those can then give you an estimate of the distribution, right? And can tell you how certain or uncertain is the prediction. Now, the first question is, how good are these uncertainties? And at least for the first one, for this predictive entropy that I just showed you, you can tell from this paper here that in general they're not very good. And why is this the case? So this is just an indication. This plot here shows that if you use a deep neural network, for example, like LeNet, which is actually a smaller one, right, not that deep one, and if you then have a histogram of confidence values, that means you simply count how often is the network how confident. Right? So for every value between 0 and 1 in the confidence, you just count how often is it that confident. For example, 80%, if you say this bin here, 0.8, right? This counts all the cases where the network was 80% confident about its prediction. Now what you can do is you relate that confidence number with the actual accuracy that the network has, right? Because you have the ground truth, you can compare the ground truth and can then tell, was it really that accurate in those cases where it said it was 80% accurate, right? And what turns out is that the smaller network here, the LeNet network, does that quite well, right? Does a good job in relating the confidence, the estimated confidence, with the true accuracy or average accuracy. Now, the interesting thing is that the deeper the network seems to be, this is what they observed here, the less is this correlation, the less works this correlation. And in the and actually, it's the opposite. So it's like the network tends to be so-called overconfident. It means that it has certain confidence values, right, where it thinks it's confident, but it's actually not accurate, right? So the accuracy goes down with the same confidence estimates, right? So in this bin 0.8 here, there are now less samples that are that accurate. Okay, is that clear? I hope this is clear, right? You just have fewer cases where it's actually 80% correct. And you should have 80% because you think you're 80% correct. And this is bad because, and the interesting thing is that the error itself goes down, right? The predictive error is good, right? Networks are better when they're deeper. The deeper networks are good. But in the fewer cases where they're bad, they are overconfident. And this is actually a problem because you have maybe fewer cases where you're wrong, but on those cases where you're wrong, you shouldn't be overconfident. You should at least know that you're wrong, right? And this is the problem here. So entropy is actually a bad measure for this predictive uncertainty because you see that if you do that, then networks tend to be overconfident. So what's another idea? And another idea I'd like to show you is the so-called Laplace approximation. Laplace approximation works in the following way. let's look again in our network, right? We have our training process, and after the training process, what we get out is a set of weights that optimize our loss function, right? This is what we do. Optimizing loss function means computing the gradient and finding the place in the high-dimensional space of parameters where the gradient is minimum or zero, right? We want to have the maximum of this gradient, of this function in the loss space, and that means we have to minimize the gradient. So the idea now is to not just have this one set of weights that optimizes the loss function, but go around in that vicinity of that optimum and say, well, there might be other vectors or other weights that are also similar to the best one. They're not, and they might not be too bad, right? They might be a bit worse, but not too bad, right? That means what I do is I stick all these weights into a vector, right? This is my mean vector. And you can guess already, if I have a mean vector, then I have also a covariance matrix, right? This is what I do. I have a normal distribution that has this mean and this covariance matrix, right? This is my normal distribution. And that normal distribution approximates my log likelihood function around the maximum, right? I maximize the log likelihood function, or I minimize the negative log likelihood function, whatever. It's nicer to show with positive because it looks nicer. And what I do now is I place this Gaussian distribution here, this normal distribution, at the maximum, right? And the only question is now, how do you decide which kind of covariance matrix I use? So how do I compute that covariance matrix? And it turns out, and I'll show you that on the next slide, why this is the case, it's a good choice to use the so-called inverse Hessian of the log likelihood function as a covariance matrix, right? Because that relates curvature to uncertainty or to covariance, right? So a high curvature, right, in this case, is a low uncertainty, right, because the thing is very peaked, yeah? And then I'm very certain about that. And if I have a low curvature, I have a high uncertainty, because then I don't know exactly where I am, right? I can just move around and everything is more or less equally good, right? So this is the intuition behind that. Now let me, in one slide, show you how this works and why this works. I have one question now for you. The first thing is, what you do is you apply the Taylor series approximation. I think most of you should have seen that before. And you do the second order of that, right? The second order Taylor approximation. That means all the third order and everything above that is just gone, right? We just, this is why we approximate this here. And we take, this approximation. So what this means is we have, of course, the first order and the second order term. Now the question for you is, where's the first order term? The first order term is vanished because the first order term is the gradient, and the gradient is anyhow zero because we had the maximum, right? So what we do is we say we develop this Taylor approximation at the maximum of the gradient, and that is, by definition, the place where the gradient is zero, right? It means the first order term is zero, and we don't have to care about that, right? The second order term, of course, is not zero, right? This is the second derivative of our high-dimensional function, and that means we have to derive that twice. And we do this in the following way. We say, well, this H matrix is this distribution of the weights given the data, given the training data, derived twice, right? And that means we get this matrix, right? So this is called the Hessian matrix. And if you look closer to that one, this is again a posterior, which we can then split down into a likelihood and a prior. This is Bayes' rule, right? Simply saying, well, this is the product of this times that. And because we are in log space, this is a sum, right? This is all we do. So we just apply Bayes' rule here, and that means we have a sum of two matrices. One is the likelihood matrix, and one is the prior matrix, right? Both are Hessian matrices that we compute here. Now, the second step we do now is we take the exponential of that equation, right? We take on both sides the exponential. That means our distribution, our posterior W given x and y, looks roughly like this one here, right? This is proportional and approximately, right? Proportional because we have a fixed add-on here, which then turns into a product, right? If there's a plus sign here and we take now the exponential, then we have a times sign there, right? And that gives us this kind of expression here, and we can already guess where this is going to, because this very much looks like a Gaussian distribution, right? With the only difference that here we don't have an inverse, and we don't have the normalizer. That means because this is proportional, we can multiply it with other things so that this actually is a normal distribution. That means we can normalize that, right? We can compute something that normalizes this right-hand side. so that we can then approximate this, this posterior with a normal distribution at the position W hat, which is our gradient maximum, right? Which is where the gradient is 0 or minimized. And the covariance matrix of that normal distribution is actually the inverse of this Hessian here, right? Because this is just what the normal distribution, the equation for the normal distribution looks like. So now we're done, right? Now we have our nice approximation. We can do that, right? And can now use it to do predictions. Again, remember, we wanted to actually compute this distribution here. This is what we want, the predictive distribution, y star given x and y and x star. This is what we had in the previous slide. Now, how do we do that? Well, now with this new information that we have, with our distribution on the latent space, we can use that, right, and just marginalize it out, right? Get rid of w by just multiplying it with our likelihood. This is the likelihood that we get from the network, right? We can now stick this w into the network, show it the new sample x star, and then ask it what's the output y star, right? This is the likelihood that we get from the network. And then we just integrate that. The problem, of course, is that we can't do this in closed form, right? Because it's just, infeasible. And because of that, what we do is we approximate that with a sum. So we sample from that distribution here. We sample w's, right? Many parameters. And then for every of these parameters, we just stick them here and then sum them up. And this is called Monte Carlo integration, right? We integrate this just by sampling. And the result is this one here, yeah? So you have your posterior distribution here, the blue one, and you approximate that posterior distribution at some mode, right? Doesn't have to be the global one, can just be one maximum. And you approximate that with the Gaussian. And the intuition behind this is, again, that the covariance matrix for the Gaussian is the inverse of the Hessian. This is nice and beautiful. However, there's one important question that remains, right? Imagine that you have your network with like thousands or millions of parameters, right? And that means that this vector here is 1,000 or million times long. And that also means that your matrix here that you have to compute, this Hessian matrix, is that just squared, right? You have millions by millions parameters squared, right? And, of course, you need to invert that, which is, of course, even harder, right? So this, in general, is not possible for big networks. And now the art is to make this possible, right? To actually find ways to make this feasible, right? And of course, what mathematicians do is approximations, right? How do you approximate that so that it's feasible, but still good in approximation? And I'll show you some way how to do that. The first approximation you do is you say, well, this is approximately the same as the so-called Fisher information matrix, right? The Fisher information matrix, and here you use the empirical one, not the real one. The empirical Fisher information matrix is defined as the expected value of the outer product of the gradients of your loss function, right? So this is the gradient of your loss function, right? Again, with respect to w, and these d theta vectors are very long vectors that derive the loss function with respect to w, right? This is the first thing. I'm not going too much into detail. In general, I mean, in many cases, you can assume that, especially if you have classification. If you have networks that have ReLU activation functions, then you can assume that this is a quite good approximation, right? This is the first thing you do. The second thing you do is you observe that across the layers, there's not much correlation, right? So one weight from one layer doesn't influence too much a weight from another layer, right? So this is some observation. Of course, you can argue how much that is actually holds. But in general, you can say, well, you only want to look into weights that correlate between the layers and not across the layers. That means you assume that across the layers there's a zero correlation, and that means this matrix here is zero across these layers. And for every layer, you have just one block. That means you have a block diagonal matrix where every block corresponds to a layer. This already helps a lot, but then there's things that you can make even more interesting, more efficient. The next idea is to leverage the so-called Kronecker product. The Kronecker product is a product of matrices where you just use one matrix to pad another one, right? You just use any value of the left matrix, multiply it with the right one, and then pad it and put it in so that you have a big matrix that is just size as big as both summed in square, right? If you have this is n by n and this is m by m, then you have this n plus m times n plus m, right? So you just have this very big matrix. It's a very nice operation to make bigger matrices smaller and then just turn that into smaller products. And you can show that this is possible for this kind of functions here because you have, in the network, you have these inputs for every layer that come from the left, and you have the gradient that comes from the right, and it's basically nothing else than reordering these gradients, right, that you have here per layer, right? That means you just have a different ordering of the multiplication, and it makes it a bit more efficient. This is nice, but now comes another approximation, and that is interesting to see, right? So now you say, well, this is approximation approximately this times that, right? And the question is, how good is that approximation? The reason why we do this, I'll show you that on the next slide, is it makes things much more easy and efficient, and now we can do all kinds of nice tricks in math and stuff like that to do that, right? However, the question is this a viable approximation? And it turns out that it's actually very often not really good, right? You do this because it's not, it's arithmetically it's nice, and I show you that, but later we have to deal with that kind of approximation. We have to see how can we do this better, okay? So for the moment we say, okay, this is a viable approximation. That means we have matrices A and G. And what do we do now? Well, we leverage the fact that we can diagonalize these matrices, right? These are PSD matrices. That means we can compute their eigenvectors and eigenvalues, right? We can do this for F, right? And I show this graphically. And of course, you can do this for A and G as well. You can prove that this is possible, right? That these matrices can be diagonalized, can compute eigenvectors and eigenvalues for both of them. And now comes the very clever thing. The Kronecker product distributes with the matrix multiplication. And this is very, very cool. What this means is you can now reorder that in this following way. You can say this is approximately the same as UA times UG in Kronecker product times SA Kronecker product SG times UA transpose, Kronecker product, UA transpose. This is really cool. This is amazing, right? Why does this work? Well, this is math, right? This is the cool thing. And now you have this, right? You have, again, a product of three matrices, and you can now relate one to the other and can say, well, if that is approximately the same as that, then we can say, well, then V should be approximately the same as that left thing, lambda, approximately the middle thing, and this V transpose, approximately the right thing, right? Right. So this is the key idea of the Kronecker factorization technique in Laplace approximation, right? It turns out, of course, that this Kronecker product is itself a diagonal matrix. This is nice, right? So diagonal, if you Kronecker factorize two diagonals, then you will have a diagonal. However, this here is not necessarily an orthogonal matrix. This is kind of a little caveat. But now what you do is, you can say, well, I have now an approximation for my eigenvectors, right? I can approximate W with UA times UG. That I can leverage to solve that equation for lambda, right? So I solve that equation for lambda and compute values for lambda and say, well, lambda should be V transpose times Fi times V, right? And that means my eigenvalues should be something like, and this comes from the equation from the Fisher information matrix, right? I just showed you that before. What I now have to do is I have to simply multiply V transpose with the gradient and square it, right? This is an easy operation to do because you can do this element-wise. For every element, you can just do that, right? That's easy to do. Now you have a better approximation of your eigenvalues of lambdas, and those you can stick in instead of this bad approximation, right? Instead of SA times SG, you put lambda in here, and this can be shown to be a better approximation than this right-hand side. Okay? So this is the main idea. And now comes our idea. So in our ICML paper, we actually found out that we can do this even better, because what you see here is what you did here now is you put, of course, the correct eigenvalues of F, but still the F, what it comes out, is not good in the sense that the diagonal entries of that F are not the same as one of the true ones, right? Thanks. So that means what we can do is we can add a diagonal matrix D such that the result of that has the diagonal entries of the true Fisher matrix, right? This is actually possible. And I show in the paper you can read how this works. Of course, you have all kinds of other issues with that because now adding that makes it not so easy to invert, but there's techniques to do that. So this is always the hindsight behind this. Okay, results of that, if you apply that to out of distribution data, right? So this is a typical example of ImageNet, right? You train this on ImageNet where you have 1,000 classes, and these classes look like this one here with 40 million images, and the test data is completely different from that, right? It's different kinds of images, artistic impressions, paintings, whatsoever. So you do that here, and then you see how well your method can actually detect that this is a new thing, right? This is OOD, out of distribution detection. And if you compare that, this is the right-hand side here, to the standard state-of-the-art, you can really tell that ours much, much better can separate the known from the unknown, right? This is the known classes, and this other thing is the unknown classes. In the last 10 minutes, I'd like to show you one more idea how to do that. And to do that, I go back to the very first lecture of machine learning. This is actually from one of the first slides that I showed in my lecture. To answer the question, is there a better method to do that, right? So if we look again on supervised learning, we have classification, we have regression, and the classification actually is separated into 3 kinds of classification techniques, right? The first one is discriminated functions, which is not at all probabilistic. This is what I showed you before. You just have this if then else. The second thing is the so-called discriminative model, where you estimate a posterior for each class, that you have this probability yk given x. This is what I just showed you. And now the third thing is the so-called generative model, which kind of turns things around, right? You estimate, instead of the posterior, you estimate the likelihoods for every class. These are the class conditional likelihoods. And then you use Bayes' rule to do the posterior. Now the question is why or what is better, right? If we want to do OOD detection, what is the better idea? Well, it turns out that this right-hand part is actually quite good idea, because if you can generate data, and this is the key part of generative models, you can generate new data from a given input. You say, give me class A, B, C, and it generates that artificial data from that class. Then you can tell things apart more easily, right? Because then you can better tell whether something is new or not, right? So if you cannot sample data from a certain class, then it's very likely a new class, right? This is easier than in this discriminative case, where you have to compare classes with each other, right? There you have to go through all the classes and say, which is the most likely class? Oh, there's no class that is very likely. Well, then it's new. Here, you don't have to do that, right? And this is the key thing with generative models. Generative models is a very hot topic at the moment. Many people are working on that, and I just name some of the methods that are around there. You pick your favorite one that you like, and they're all very powerful, right? This is the reason why people work on that. GANs and, I don't know, diffusion-based models, variational autoencoders. All these methods kind of belong to this big class of generative models. And I'd like to show you one thing, and I think this was the class question yesterday, a recent work on normalizing flow, how to use normalizing flow and what this is and how to apply that. The idea here is quite simple. So you have a function between the data and some latent space z. So your data space is x and the latent space is z, and you want to learn a function that maps from x to z such that you can sample from z and generate data in x, right? So you can just invert that. That's the main idea. So you have random variable x, which is data, then you have your CDF, the cumulative distribution function, that tells us the data, right, which we may not know, and you have a random variable z that is the mapping from x to z with this f. And of course, what you need is a so-called diffeomorphism. That means we have to be able to invert f, and the inversion should be differentiable, of course, right? We'll see later why that is the case. How do we do that? So our CDF of z is, by definition, the probability that z is smaller than a given value small z, right? Now we can apply our f function. That means for every element in z, we have an image so that we can map it to z. That means we can say this is f of x, right? For every z, we have such a value because it's invertible, okay? And that means if we can now apply our function on both sides, we can invert that, right? We can invert this on the left-hand side. That means that the probability of x given that x is smaller than the inversion of f of z, right? And this, by definition, is just the CDF, the cumulative distribution function of x, right? Where we cumulate between minus infinity and the border and the place where this is given, right? This f to the minus 1 of z. So this is that, and now what we do is we derive this on both sides, right? And of course, if we derive the left-hand part, then we get, of course, the PDF, right? This is the derivative of the CDF. And the right-hand side can be derived with the chain rule. We simply say, okay, if we take the chain rule here, then it means, okay, we have the integral here, and this is the fundamental theorem of calculus. That means the derivative of that, of the integral is exactly the function itself. That means we have that derived with respect to z is p of what's inside, and this is basically our border here. This is this thing here, right? We just take that. And then the inner derivative, which is simply the derivative of the inverse of f, right? That's it. That's it, chain rule, nothing else. And that is the so-called change of variable formulation, right? Then we can reformulate that. We can say, well, this part is actually x, right? The inverse of f is x, right? And we can resolve for x and can say, well, this must be p of x. And then we take the inverse of that, and then we have a rule to generate data, right? We can sample from z now, sorry. We sample from z, multiply that with this inverse derivative of f, right? And then we have samples of x, right? We can generate data. And in the multidimensional case, this is this one here, right? So we have just vectors instead of single values, and we have, of course, the determinant and the Jacobian matrix because we have many entries. But that's it, right? See, it's not that. And it's the inspiration taken is this one here. This is actually a figure from Bishop's book where we can sample from any random distribution, right? So this is the same idea. You have some kind of PDF, p of x, that you have given in closed form, and to sample from that, you sample uniformly on z, and then apply the inverse CDF of p, right? This is the same thing here. You can prove that this actually works when you take the inverse CDF of that. So that's basically sampling from that distribution. Now, how can we do that? How can we use that? We can use it, for example, if we have a training data set like this one here, and learn a function into this latent space. And this latent space is, if it's a good idea, is to use a Gaussian distribution again, right? So we map this to a Gaussian distribution in the latent space, and once we have learned that, we can invert it and can then generate samples from the Gaussian and then generate data in our data set, in our data space, right? This is the whole idea. In the paper here of Din et al., they show how to do that because it's not that straightforward, right? It's not just any network that you do, so we have to play a lot of tricks because it's, of course, not so easy. You have Jacobians again with large sizes, and you have to do that efficiently. They use so-called affine coupling layers. They use checkerboard methods and the multi-scale architecture. I recommend to read this paper. It's a nice paper. It's called Real NVP, Real Valued Non-Volume Preserving Methods, right? This is the architecture that they use, and it's available. You can just use it and try it out, and you can make this kind of nice figures here. Now, the problem is very often it doesn't work that well because you still have this problem that if you have multimodal distribution in your data space and you want to map that to a Gaussian, which is unimodal, then you have this kind of topological mismatch, right? So you have to split distributions into many modes which come from one mode, and it's shown that it's not so easy. The performance of that is not very good because you have this constraint that your function f must be invertible, and that makes things difficult. And for that, there's another idea in this paper here shown where instead of using a Gaussian distribution as a base distribution, you can use other distributions, so-called flexible multimodal base distributions, and they call this resampling base distribution. So you learn the base distribution together with the flow, right? So you have the flow mapping, this f, that you learn anyhow, but together with the flow f, you can also learn the base distribution. And the method that they do is called LARS, right? This is a learned acceptance rejectance sampling. It's a nice name for an algorithm. So you simply have a generator P, and then you have an acceptance function, and that acceptance function has, again, parameters that you can learn, right? It's basically like any kind of sampling technique that you have. And this acceptance function then have learned parameters, and that means you have both now. You have the distribution that is learned and the flow that is learned at the same time. This is called RBD, right? However, come on, there's still one problem here. If you want to do this for classification, then these RBD distributions, these are class agnostic. We have one distribution for the whole thing and not for each class. And in this paper, which we're going to present this year at COL, so if you're at COL, please come and have a look at the paper. What we do here is we have so-called class conditional RBDs, right? We learn for every class a different one. To model these distributions more precisely, right? However, this brings other problems because then we have this trade-off between very precise locally on the classes and very good at the general density estimation, right? If the general density estimation has different subjects, right? So they contradict a little bit, right? And to solve that, we use the so-called information bottleneck, right? It's basically something where you have the mutual information between the latents and the labels, and the latents and the order distributions, right? So you kind of make have another objective function that kind of trades off between the class learning, right? The class specific learning and the density estimation for the whole density. We have an example here where we train this for 2 classes in BlenderProc. We generate samples here for 2 classes. These are called Valve, and we have a small robot that is called the crawler. So that means we have 2 objects that we want to classify and tell apart. And yeah, this just shows you a toy example how this looks like, right? So we have 2 classes here which are distributed in this kind of 2 rings, right? Which is of course very difficult for a Gaussian, right? With a Gaussian you can very hardly model that, right? And with our model, you can show that you can actually do that, right? So this is our class conditional RSB here, what we use here, and you can show that the estimated distribution that we get out of that look pretty much like the ground truth here, right? Now, if we apply that to a real problem on a real system, then the results are the following. So we have this implemented on a system with an NVIDIA Jetson. And here, this is just showing how much resources we take, and it shows that we don't take much more resources. So we compare that to a standard object detector YOLO version 5, version 7. And we just add our out of this distribution detection on top of that, right? We say, okay, give me the objects with YOLO version 7, and then we add our OOD detection, and we can show that and this curve here is this so-called ROC curve. That means it's ideal if it's just going up here directly and then going right. So we need this kind of hook, right? We need to go this up and right, because at very low false positives, we want to have high true positive, right? And this just means true positive, is it really out of distribution or is it not, right? It's a 2-class problem that it detects us whether we are OOD or not. And this is showing a small video how this works. So we have this environment here where we have these valves, and this is an inspection robot, right? So we have these pipes here, and we have a small magnetic robot that goes through the pipes and inspects that. And our system now is implemented on that system here, right? Where we have a camera that observes the scene from above. And these are actually simulations, right? These are from Blender, right? We simulate classes here, and we can show that the simulated classes, if we show them in inference, then we get a higher likelihood, and that means we know these classes, right? We have trained on them, and we know them. However, if you take the image from the real scene, then things look much different. You'll see this later. Now this is the real scene, and suddenly we have lower likelihood because now the crawler looks much different, and we have a threshold that is also learned in training, right? The threshold that tells us, is it new or is it not new, right? Do I know that or do I not know that? And that threshold can then be used to tell things apart between known and unknown. Now, I come to the conclusions. I want to show you that there are 3 problems in perception that need to be done for manipulation, and these are object detection, pose estimation, and graph detection. And to do that, we have these kind of problems. We have to cope with inverse problems, and inverse problems we can deal with so-called learning methods, right? Deep learning methods, of course, if you, in best case. And it's just filling the gap with data, right? And then I showed you also how to address this open world assumption, how to find objects that are new, and how to detect that they're new. So we have this OOD problem, out of distribution problem. And I showed you BNNs, how to do that using Laplace approximation. I showed you also an example of a generative model, right? That's a recent work using normalizing flows. And how to do improvements with this kind of class conditional modeling. And before I end, I'd like to show you that. If you're interested to work with us, please contact me, because we have a very exciting project here. This is a wheelchair called Eden. And we actually plan to do a cyberthlon. I don't know if I can show that. So in the next year, in 2024, during the whole year, there's one team member who will not be with us, and we really need someone to replace that person. So if you're interested, and if you are really interested in doing perception on this kind of wheelchair, please contact me. I think it's quite cool to do that. We have all kinds of exciting topics on this project. Just contact me. And with that, I thank you for the attention.